Lesson 1, part 2. We were on example 2, and it's just another scenario of how we could do this. We have two different hypotheses this time. The null hypothesis is that the population mean is 5, and we're comparing that to the alternative where it's just something that's not 5. So at alpha being 0.01, at that significance level, we are testing our sample. So it was sample size 37. The population of interest had these particular mean and standard deviation, where you get to just assume that the conditions are met. We don't have to test it this time. First, I just want to know, why do we have some evidence for the alternative? So again, the alternative says that the mean is not 5. So if you look, the sample mean was stated to be 4.81, which you might notice is not equal to 5. But that's what the null hypothesis is suggesting. So we have some evidence that the alternative hypothesis might be true. So there's some evidence. We are now called upon to test it, and we're going to do that by calculating the standardized test statistic and then finding the p-value associated with that. So our t, standardized test statistic, is our sample statistic minus the population parameter assumed to be true in the null, divided by the standard error of our test statistic. So divided by 3.65 over the square root of our sample size. We're going to get a negative this time, which is okay. We do need to care about the direction of this test. This particular test is a two-tailed test. So that would mean, let me see if I can, I'll zoom way in and I'll sketch it here. So this would be like having some t-distribution table. We have our test statistic of negative 3.17. That would be the area over here. But you can also consider, you also have to consider the other tail because it's a two-tailed test. So the other tail of positive 3.17. These two areas combine to make our total p-value. And this, again, I just sketched a t-distribution. Specifically, we have to note our degrees of freedom, one less than our sample size. This has 36 degrees of freedom. Oh, great, here comes a kid. So we're going to use the table for this. I, again, snipped in a table so we can talk about it. It's not the whole thing. I chopped out the middle portion of it. But we are trying to find now this test statistic on our graph, on our table. Now, they're all negative, so we're just going to look for the positive because it's symmetric. So when I go looking for 3.17, I first have to care, though, about our degree of freedom. I have to be on the 36 degree of freedom line, which you'll note this does not have. So you can't just round up because that's essentially cheating. That's like assuming you have a bigger population size than you actually do. So I have to round down to 30. So I'm stuck in this row. And again, I'm looking for a test statistic. Now I'm looking for 3.17. I don't see it, but I do see 3.03 and 3.385. If I look at the areas that those correspond with, that means our p-value, not our p-value, the area in that one tail between these two numbers. So let me write out what I'm trying to say here. So the probability of getting a t-value that is greater than or equal to the positive test statistic. This is something between, we just saw 0.001 and 0.0025. Ben, take it outside, talk to your daddy. Now, that's just one tail. That is this area up here. We have the exact same area over here. So that's not our p-value. That's half of our p-value. So when I talk about our p-value, that's the same thing as the probability that that test statistic is to the left of negative 3.17 or to the right of positive 3.17. No, I ask you to talk to your daddy. Please take it up. Well, then shut the door.
Ben, let me see him. Ben.
So we still don't have exact values that we can get from here, but we can say what it's between. So I'm going to double both those endpoints. When I said endpoints, I mean areas. So our p-value is somewhere between these two areas here, which is real small. So in this instance, because it's less than the significance level of 0.01, you would get to reject the null. This is really unlikely to get a sample with this dramatic of a test statistic just by chance alone. It's much more likely that the null hypothesis is not true in favor of the alternative, that it's just not 5. We can and will use our calculator to find these values. So if I go back to the first one we did in the other video with a test statistic of 1.55, that was a right-tailed test with 14 degrees of freedom. Now, I don't want to use inverse t because I'm not trying to, what am I trying to say? I'm not trying to find the test statistic, I'm finding the area. So if you remember, we used to find areas with normal CDF. We're not talking about a normal distribution though, we're talking about
8 times with
the t distribution. So I don't want normal CDF. Most of your calculators should have a t-CDF. I'm pretty sure even those of you without an inverse t will also still have a t-CDF. So go looking, even if you're sitting there thinking like, well, this doesn't apply to me. Good chance it does. Look. So t-CDF, I said this is a right-tailed test with, I think 1.55 degrees, sorry, 1.55 is our test statistic. So I'm going to say to the right, and I already forgot our degree of freedom. So let me write out actually what I'm doing. We're doing t-CDF. The lower value is our test statistic of 1.55. The upper value is just something huge because we would like it to go to infinity. And this one had 14 degrees of freedom. I'm really curious how many of Mr. Dresch's stupid comments in the background are coming through on this video. So 1.55, and why is that so dark? There we go, 14 degrees of freedom. So when I put that in my calculator, I get the area of 0.0717, which corresponds to what we saw in the table between 0.05 and 0.10. So now if we're doing a two-tailed test with this test statistic and 36 degrees of freedom, I'm going to double the area. So I'm just going to go ahead and throw in my calculator t-CDF. Since that's a negative, I can still use the negative and just go below that one, or you can flip it and use the positive and go above. It will not matter. But we're just going to denote that we have 36 degrees of freedom. Let's see if I prop this up if you can see it any better. There, more dramatic. So, I already forgot what I was writing. 2 times t-CDF of the test statistic that I forgot. Negative 1,000, 3.1. I think it was 36 degrees of freedom, 37 degrees of freedom. 0.0031. 36 degrees of freedom. So this, and I already doubled it. I did that first so I wouldn't forget. It's very common to forget to double it. Always pay attention to what type of test you have because it's extremely common to forget to double when you are finding the p-value for a two-tailed test. Which means we're ready to do all the steps for a one sample t-test for a population mean, because it's not that different than what we had been doing. So, the level of dissolved oxygen, denoted DO, in a stream or river is an important indicator of the water's ability to support aquatic life. A researcher measures the DO level of 15 randomly chosen locations along a stream. Here are the results in milligrams per liter. So we have our sample data. An average dissolved oxygen level below 5 milligrams per liter puts aquatic life at risk. So we're going to test to see if we have convincing evidence at 0.05 significance level that the aquatic life in the stream is at risk. So we're going to go through our 4-step process, starting with, we're going to state what we're doing here. So we would like to test, and I'm going to state my hypotheses. The null hypothesis states equality. We are testing whether the population mean DO level is 5. we're testing to see if it's at risk. It's at risk if it is something, where does it say? Below 5 milligrams per liter. So we're testing that it's below. We're going to assume that it's 5 until we can prove otherwise. But I can't use any type of variable without defining it. So where mu is the true mean value. You would have thought in the time I made these 2 videos, I would have stopped and wrote all this out so that you don't have to sit and watch me. Clearly, that is not the case. So define your variable, but also go ahead and say the significance level that you're using. So that's our state step. Then we're going to plan out what we're about to do. This is called a 1 sample because until next lesson you were only doing 1 sample at a time. But it's a t-test, and the thing we are testing is not the proportion but the mean. So we got to test our conditions in this step. So the first one is the random condition. Did this sample of 15 come from a random sample? And it does say that somewhere.
I got wet because Ben pushed me down the slide on purpose 2 times.
Are you going to make it? Hey, go shut the door for me and then go change your clothes.
But I don't want.
What else? I don't.
I need your help.
You're on video right now. All my high school kids just got to hear that